Thanks, Andrea. I think you did a very good marketing pitch for TAPI. So if I'd known, probably I would have cut my slides. So my slides have it in two parts. The first part is just non-technical, just telling what TAPI is about and where it's being used and generally just information. And the second part is a little bit technical, gets into a little bit concepts of TAPI. The whole idea, at least I thought, was to introduce folks to what really TAPI is and what are the key concepts that you would want to know, because it's slightly different than what you might be used to looking at when you talk about APIs. So the initial introduction, the first problem statement, this is like we started TAPI like a couple of years back, and it was like, okay, why we needed to do this? And at the time, like we had like different controllers platforms like Open Daylight, ONOS, and each one had their own northbound APIs. And then we had in at least transport domains, right? TAPI stands for transport APIs, by the way. We had existing systems, EMSs, NMSs, that were not going to go away anytime soon. I mean, we knew that. I mean, the folks here, like, we knew that it's not going to be a greenfield scenario. It's actually going to be a slow brownfield scenario for introduction of SDN. So now we had all the systems in here, each one with their APIs, and then people were like talking about building this network orchestrator those days. And now this orchestrator has to talk to all of these different platforms using different APIs, right? And this is just basic APIs. Now, if you're thinking of developing apps, right, forget orchestration, and you have some idea for some kind of app, first thing you would need to do is at least like understand all these APIs to all the systems, right? Figure out how you're going to abstract that out. And by the time you've done figuring all this out, it's going to take quite some time. You're probably going to give up because it is a lot of work here, right? Just understanding all these APIs, how you're going to abstract all that out and, like, you know, to your application, and then code it in such a way and so that you can actually deploy this across these platforms. So some of us, like, who were looking at doing this, we said, oh, we need to have a standard API here, at least for transports. The applications we had in mind, not everything, we don't try to address everything in the world, but at least the applications we had to have some common abstractions. So that's where we started out. So with TAPI, we don't go and try to prescribe how your system should behave internally, right? It's an API, right? It's a transport API, it's an interface. So it's kind of like we assume this, your controller systems or your SDN or EMS, NMS is a black box. We only look at the interfaces on the top. And then we try to develop different, I would say, abstractions and functions that we thought would require to be exposed in order to develop various applications. So how we did that is, rather than focus on how something is implemented, we said, okay, what does application need? If you're going to write some kind of applications, and the first one was like bandwidth on demand, what do you really need it to expose, right? What kind of information you needed from your network? So first thing we said, oh yeah, you need to know the topology, and you need to understand how things are connected to each other before you can actually figure out how you're going to set up your bandwidth, right? So we started with topology service, and then connectivity service is the service that lets you set up connectivity or request connectivity, right? I wouldn't say set up, it requests connectivity, and you let the black box figure out how to set up the connectivity. And then, of course, anything to do with transport has to do with quality assurance, SLAs. So this was the OEM service. Go back. And of course, now we had some use cases where we had this use case where you could just request connectivity from your black box transport API provider, and it would compute the path and give it to you, but then that was very simplistic use case. In a real scenario, you had like different vendor islands, you had operator administrative domains, and then you had to have some end-to-end view of this entire ecosystem, and you needed something on the top. Now, to do this effectively, it had to be a two-step thing. Like, you had to ask your individual domain controllers to compute some paths given some parameters. You collect all this from all your controllers, and then you figure out what is your best path end-to-end from the top, right? So we had come up with the path computation API. And finally, we had a virtual network service API. This was kind of the original use case of TAPI, but to be honest, we found that it didn't really take off there yet. Once we started doing this, because this was the SDN, right? We worked in ONF right from day one. So we are looking at virtualizing transport networks, but once we went down this path, we started getting questions about, from the operators, okay, that's fine, that's great, but we need to solve the problem, the simple problems today, like setting up connectivity, topology. We don't have a common interface. So the last 2 years, at least, we ended up focusing exclusively on, I would say, legacy applications, which was not what we started out. We wanted to do like virtualization and so on, but we never got there. So we sort of put off on the virtual network service from initial, whatever we had, and we focused more on these other APIs to sort of put more features in that the operators were asking for. Right, so we did the standards in a little bit different way. It was not our traditional way of doing standards where you publish paper specs. We used a lot of software, I would say, processes. And one of those was like, we said, okay, we are going to develop APIs. We need to be able to at least provide some kind of reference implementation. So we started with the idea of reference implementation, but finally it's come to more like it's an educational tool to see how you can code the APIs and validate some of the APIs. So it's not really a reference implementation, but at least we try to do that. So we have a TAPI client in Python, and then we have a backend TAPI server, which is nothing but an emulator, network emulator, where we sort of define the test case networks in like using JSON schema, and then we serve it whenever various APIs are called. Then, since we are working in ONF, we started talking to the other groups in ONF. Like one of them was ODTN, and then we started getting the implementation of TAPI into ONOS, so which is kind of normal. But other thing is we also have an implementation in Open Daylight. It's called Uni Manager. It doesn't do optical. It does like more like carrier Ethernet services, and we'll get to that later. But there is an implementation of TAPI on Open Daylight too. So now in ONF with TAPI, we are developing the specs, but one way we did it is, like I mentioned, we're doing it in agile fashion. So we are iterating. So it's kind of a living spec. It's not something we took 3-4 years to develop and then stopped. We within like 6 months or so, a year, we had an agreement with OIF, Optical Interoperability Forum, to actually have an interop of the APIs and see how it could work. So with TAPI 1.0, we actually had an interop in 2014, which was precursor to TAPI. Actually, it was one of the reasons of developing TAPI was out of that effort, where we didn't have TAPI at the time, but we kind of realized that we needed something like TAPI as out of that effort. That was more of an open flow optical extension interop. That was 2014. In 2016, we interoped the TAPI 1.0, and in 2018, we did an interop of TAPI 2.0. And these are the various vendors involved and the operators, labs in all of these interops, various other interops. So, and if you look at this, one thing that you would notice is that, again, this grew out organically. This is not like by design. We found that TAPI was more or less always applied in top of the controller NBIs, what we call NBIs. And the reason we didn't use the word NBI is you see that the TAPI is used depending on where your controller is, where your software is. It could either be consuming TAPI as on its SBI, or it could be serving TAPI as its NBI. And so this is one of the architecture that was used in one of the operator labs. I think it was Telefonica labs, where you had this hierarchical architecture where you had multiple domain controllers. And the use case was like, this is what they were visualizing at the time is this was Telefonica Global. They had systems all across the world, and then there was this local domain controllers they would have in different regions. And then you had vendor domain controllers, vendor islands, which were serving it up. So then they had this need for validating whether such kind of hierarchical architecture would work. And in this, we actually demonstrated you could use TAPI recursively and actually get things done in a reasonable time frame, in like few, I would say, minutes, few seconds, to actually request bandwidth on demand and get it done. Of course, even in the seconds, like most of the time was actually spent on, was actually for the optical equipment to tune the optical equipment, not so much as the APIs sending the requests and getting the responses, but actually like once you turn on the transponders and so on, it would take some time to stabilize. That's where even like 30 seconds, most of the time was spent on that. So now looking at another aspect of TAPI, ONF as an organization, we work closely with MEF, and we co-develop a lot of TAPI features in conjunction with MEF. And actually the Open Daylight Uni Manager was actually done within MEF ecosystem to validate the L2 service interfaces. So apart from that, MEF has many projects, but I'm just focusing here on what they call the Optical Transport Implementation Project. In there, like MEF is a little bit a more traditional SDO in the sense that they have the service attribute specifications, and then you have the models and you have the provisioning interface, which finally the provisioning interface and the model is based on as extensions of TAPI. And this was the kind of network that is being targeted, where you have a mix of Ethernet and OTN services on the unis, but your entire NNIs are all optical transport networks. Right, so and in here again, this is a work in progress. We had like actually one implementation done and that was last month in MEF 18. There was a POC and it was demonstrated out there. And finally, of course, I'll skip this ODTN slide because Andrea went over it in so much detail. I don't need to look at it. So now finally, what is really TAPI? I mean, you heard a lot of words on like, okay, we did this, we did that. How do we really work? So ONF, there are a couple of projects, right? One is called Open Transport Configuration and Control, OTCC. And there's another project which is Open Information Model and Tooling, right? Now, we develop the TAPI requirements, use cases, and so on, those discussions as part of the OTCC discussions, right? So that's where you have all the vendors, optical, not just optical, but TAPI is again a technology agnostic interface. We'll get to that. We develop the use case requirements. In the information modeling project, actually, ONF, the group has developed a core information model that is actually agnostic of your interface, it's agnostic of technology. It forms as the base for TAPI, right? And the other part of the information model was technology-specific models. And the technology-specific models, the way we worked is we actually borrowed it all from ITUT. So we're working with ITUT models as of now, more or less. So for the OTN, we are using the 874.1, Ethernet 8052, and Photonic 807.1, which is kind of still work in progress. And of course, the generic ITUT model 77111. So all of these models work. Of course, the ITUT's models are not, I mean, they are in UML format. There's also specifications. It goes through a longer process of getting ratified. But we did take them up. We developed what we call specification models based on those. And all this left side part of this, you have the models. Now, on the other side, we have the open source initiatives of ONF. So I'll focus first on the Eagle projects, which we call Eagle modeling tools on the right. So there was an UML model profiles that were developed in that, so that all your UML models should be built according to the profiles which was specified in that project. And this is how we built the TAPI model. We took the profiles from this Eagle project, we applied it to all this information modeling, and we applied a process called pruning refactoring, and we came up with TAPI information model. So the starting point for us from software point of view was an UML information model. Then in the Eagle project, we had a tool, we still have a tool, we're working on it. It's a work in progress still, which takes the UML and generates YANG. So we don't write YANG by hand, we generate it from the UML. So, and then we have yet another tool which takes the YANG and generates open API specifications. And I hope everybody is familiar with open APIs. It's the latest buzzword in REST APIs, right? The way to describe your REST APIs. And then we use the open API tooling to generate Python reference implementation code stubs, which I showed up, and then we sort of boot in some test databases to test the APIs. We also, like I mentioned up in the other slides, we work closely with MEF in both the network resource modeling projects. So Andrea here is leading the NRM projects in MEF, plus the interface MEF resource profile, resource provisioning projects, which use TAPI, right? And MEF has two parts. One is the standards work, and then there's the implementation work, which I gave one example. So the two projects that in MEF that's using TAPI is optical transport and packet WAN in the implementation side. We are looking at doing SD-WAN too. It's like very early phases to see whether you can apply TAPI to SD-WAN. And we'll probably learn some things from that. And also mention that OIF is working with us very closely to actually develop, to host these interops, because that requires a lot of effort and expertise, which OIF is what well is known for. It's known to host the interops. So we don't try to do everything ourselves. So the whole TAPI effort is not one group working in isolation here in ONF. It's an ecosystem of different SDOs working pretty closely. So that's why I just put all of these slides. So feature set, I'll quickly skip over some of this. I mean, I won't go in detail, but like I mentioned, we had the topology, connectivity, path computation, notification in the first release of TAPI. Then we enhanced it with like specifying constraints so that you can actually, in the first TAPI 1.0, we assumed simple use cases where you could connect any port to any port without any constraints. But then we enhanced it so that we can now actually articulate constraints so that whether you can connect a port or not, how much capacity is available, resilience protections, OEM monitoring, and alarm TCS streaming. And all of this, one thing I forgot to mention up front, all of these on this left and up to the top is technology agnostic. So we don't develop TAPI as a technology specific interface. What we do is we develop all this in technology agnostic manner, and we add the technology-specific extensions as what we call like specifications, right? So those are extensions to TAPI. So you could use TAPI without using any technology extensions, but if you want to get down to a little bit more technology-specific details like photonic parameters, like ODTN will be getting there soon, they would apply this photonic extensions so that you can actually see the other parameters that are specific to your technology you're interested in, right? So, and you can even have a mix. So you can have like some of the use cases where one of your uni is OTN, like in MEF, like one of them is Ethernet, other one is OTN, right? So it's a mix of interface points. It's not just pure technology layers. And I'll skip these slides because Andrea more or less, I think, did a good pitch for like why you need to use TAPI. So, and it's a work in progress. So there's a lot of work to do. It's going on. So now I'm just going to switch gears. I don't know, I have only few times. So I won't go to the rest of all the slides in here, and it's available, so you can look at it, it's animated. But I'll at least explain a few core concepts of TAPI here using an example, right? So assume that you have a very simple physical network where you have 3 or 4 unis, right? And they are 200 gigs, 200 gig unis. And you have like 3 transponders, like, and I deliberately chose this thing where you have each of these transponders do a uni, and the third one is actually having two 200 gig ports, as in just an arbitrary example, right? And you have the OLS domain, which Andrea mentioned in between, which is separately managed and operated, right? For whatever reasons it's separate. Could be a different vendor, or it could be just because administratively it was a different system, right? Now that needs to interface with this transponder domains, right? And TPD stands for transponder OLS. And here the assumption is the NNI interface on this 2 sides is 200 gig, other is 400 gig, roughly, right? So now, and internally it's a network of ROADMs. And this is like a kind of simple use case to explain. We didn't just go with the open line system, even though I use the word OLS. I just put in a ROADM so that there's a little bit of switching element there, not just something there, you just string things together. Right. Now, in this, there are few concepts which is important that you understand from TAPI. So just think of an TAPI provider or SDN controller. Like I mentioned, TAPI is recursive, so you can apply it on both northbound, southbound, client server. Now, for these controllers, like each of these transponders, right, assuming this is your transponder controller, right, on the southbound, it just appears as a group of resources. And your OLS controller too is probably just another group of resources. It could have been a device very well. It doesn't know because it's software. All it does is it communicates with these, I would say, agents using some interface, which could be TAPI. So now it has a context of all this information that it communicates on the southbound. So it's nothing but each one is isolated. I just use the word device context so that you can say that from this controller perspective, everything is like a device, right? And then based on this information that it gets from the southbound, it forms some image of what its network is. Right, and that's the key thing that you have to remember is now this is a mix of both physical devices that it's talking to as well as OLS, which is a controller, right? But it doesn't know, or it doesn't have to know. It can treat both of them the same way, whether it's a controller on the southbound or it's an agent on a network element. It shouldn't matter, right? And then on the north, it's servicing 2 clients. I forgot to mention that there were like red and green clients, I assumed, 2 customers, right? So each of those customers would be provided with their own what we call TAPI contexts. Right, so each one would have its own isolated view of the network or the points that it's working with. So the whole concept of TAPI is the consumer on the client, TAPI client, doesn't have to worry about contention and so on. It thinks that it has exclusive control of the network that was provided to it on its northbound, right? And that's one important concept. And of course, you could have kind of an admin application too, which could see all of this stuff. So I put that in blue. Now it's the job of the controller internally to manage this, right? Do conflict resolution and make sure all the resources are managed properly, and there is isolation between like the client customer 1 and customer 2 traffic doesn't mix up and so on. TAPI doesn't say how it should be done. We're just providing the interface. We assume that this is how it should be done, right? So with that in mind, this is one example how you could apply TAPI, right? So you have the OLS operator view. He has a view of his network, and you have the transponder domain controller, right, which sees only the transponders. Now, I just introduced something called TAPI context. So the OLS exposes TAPI context, in its TAPI context, some information to the transponder controller, right? This is one example of how you could use it. And that could be, that's what it's called OLS domain. And this view could be a single node view. It doesn't have to expose all the information it needs. And TAPI says you expose whatever it is, but it's the same concept applied recursively. Whether you could, the node here from an information model or a structure or an object point, it looks the same as that node. There's no new extra characteristics, like we don't say a physical node versus logical node. We don't make this distinction. It's just a node is a node with ports on the edges, which is the one in purple, and some capabilities like how you can connect the ports and not connect, and what is the capability of the port. And then the same thing can be done recursively. Like, so this controller on the northbound could take this network it has and just only expose 2 unis. I mean, so the customer green context sees only one node with 2 ports, that's it. It doesn't see anything, all this complexity in, right? And the same thing the red, it just sees a node with 2 ports, right? So now if you're doing end-to-end connectivity request flow using TAPI, like DSR stands for digital signal rate, constant bit rate signal. So that's what MEF has defined as L1 connectivity service. And this is the only service that's right now actually defined in any SDO that can be actually, which has been standardized. Nobody has yet standardized an L0 service yet. So this example assumes your L1's connectivity service between these 2 unis, right? And this is kind of like a big picture view. Like we assume that we can see everything. To set up the connectivity service, first you need to set up the connectivity in your OLS domain, photonic, right? And if you're familiar with photonic technology, I hope at least many of the folks in the room, since you're here, understand this NMC, network media channel assemblies, and so on, right? So you have to set up the media channel between those 2 points first, right? Once you set up the media channel between the OLS domain, then you can actually turn up your optical tributary signals. And here we have taken a case where it's not simple OTU, but it's OTU-CN. So that's why I took the 200 gig example. So it has, if you want to keep it simple, it's 200 gig with 200 gig lambdas going through, right? To use a simple term, right? So that's what is being set up. That's called OTSI assembly connection. And then finally you turn up on your client digital signal rate, which is actually carried through it. And I've shown something small in between, that is your intermediate ODU, because if it's an 100 gig DSR signal, it goes into 100 gig ODU4, which goes into ODU-CN and then over OTSI. So this is kind of the connections that get created in TAPI domain. Now, when I say gets created, this is what is expected to be exposed over TAPI. How you manage internally, we are not prescribing that, right? Internally, you could use your TL1s and have some cross connects or not, we don't care. But this, when you say TAPI interface, we say like, okay, these are the constructs we expect if you're using photonic. This is, if you set up a connectivity like this, we expect you to expose these constructs, right? And the same thing, so the second connectivity service, you set up the second media channel, and then you turn on the lights, and then you finally put on your client signal. I don't see. Okay, I'll just spend a couple of more minutes and then wrap up, because take it all the way. Now, how would all of this look from TAPI perspective, right? If you now applied in TAPI, the first was like not TAPI views. So you have the OLS, and you have the transponder domains, and the OLS exposes a TAPI context, a single node view, and the transponder controller exposes 2 contexts on the northbound. So let's say the first connectivity service was done in the customer A domain, and he requested a connectivity service between his 2 unis. Now, the OLS and the ONOS, right now this is ONOS here, doing the transponder control. It has to compute path. It has to figure out now, given this topology that I see, because he sees the topology in here, how do I provision the path? And assuming he does that, he then makes a connectivity service request in turn to his southbound, right? His server controller, saying, hey, I need connectivity between these 2 NNIs, right? And then once the connectivity is realized, then there could be another connectivity service coming in. The ONOS again translates that into another southbound connectivity service request and serves it. So now adding all the resource view, you have the first connectivity service, you have the photonic connectivity service going down to the OLS domain. The OLS domain provisions the media channel, returns back the response saying, hey, I created the media channel. So the transponder controller sees that information in his domain. Yep, 5 minutes, yep, I'm done. This is the last slide. I'm going to stop here. And once he sees it, he's going to then turn on the lights and provision the transponders, and then provision the end connection and return it back. So I'm going to stop here. I'm not going to go into there are some other scenarios that you could do. Alternate ways of representing it, like which I just called it an orchestration view. Instead of having this hierarchical control domain where you have ONOS or like a transponder controller as a client, you could have a service orchestration controller that sees both the transponder domain and the open line system controllers. It treats them as peers and it sort of does end-to-end. So that's kind of a little bit more realistic. I would say in a network operator, this is the kind of situation you might see. So then each of these domain controllers are independent. I would say transponder does not really talk to the OLS, and the OLS does not talk to transponder. They just talk to a service orchestrator, which does the big picture view. So you could apply TAPI, and there are a few other ways you could architect TAPI to be used. And I won't get into this, but it just basically tells you how you can do this. And this is kind of what was done in phase 1.0 without doing the OLS. And I'm going to stop here. How do we exit? Just do enter. Yeah, I'll not go into this. And if you're really interested, just look at the links. I put in some references at the end. And this slide deck is available on my ONF Connect page. I mean, there was a page that was created for this session. I just put it in. All of it is open. We work as open source project, so there's nothing closed. Any questions I can take? No.
Any questions for Karthik?
Mm-hmm.
Karthik, is there any other alternative to this? How does this compare with stuff that's done, for example, in the IATF?
Just different philosophies, different SDOs doing their own way of doing things. But the main difference, at least from IETFTs or anything, was they started with the starting points were different, right? So the goal of the T's was traffic engineering database. It was to expose the traffic engineering information out. While we started TAPI with doing the virtual network service. That was our starting point. Oh, we need to do virtualized transport network. We started out there, but then we realized, okay, there's really a lot of work needs to be done in the plumbing first, and that's what we are doing. So eventually we might converge, we might be addressing the same use cases. That's kind of what I realized talking to people. Like there are like common use cases now, but the ecosystems are different. In IETF ecosystem, it's all IETF models, IETF trying to support more or less whatever has been developed out there. Out here, like it's an MEF, ONF, OIF, ITUT ecosystem. So in some ways, IETF is working on its own. It's pretty huge, while we are working more collaboratively because we are smaller. Yeah, Nigel?
Just going to add to that, one strong distinction is, I think what Karthik said is the starting point with service. You end up with a bidirectional fundamental concept that can then be supported with unis, whereas IETF started off with unidirectional as the initial thing, and then they had to assemble it into bi. So those two philosophies end up with a different sort of a pattern. My personal view is bi first and then going to uni is the right way to do it, but because you can always turn a bidirectional thing, which is uni bi into as little unis. It's much more difficult to collect together loads of unis and then with a load of pointers and references make them seem to be bidirectional. So I think that's the big distinction between the two models.
Yeah, there are a lot of technical differences. I didn't want to get into that, but yeah.
Okay, right. Then I shouldn't have said
but that's because of where we started and where we're going.
Yeah, that's right. It's the starting point that made the difference.
Yeah.
Okay. Let's thank Karthik for the presentation.